Next up, we have Hannes who will talk about utilizing machine learning optimized polynomial partial piecewise polynomial models in mechatronics.
Thank you. Yeah, good day to you all. I'm Hannes Waclawek and I'm a doctoral student, currently starting my PhD. As Simon pointed out yesterday, this workshop is kind of a mix of people who present reinforcement learning focused topics, and I'm now one of those that are more in the generalized optimization setting. And although we are now just in a plain gradient-based optimization approach, I already see how powerful reinforcement learning is with optimizing real systems. So yeah, that's what I want to do in the end. So we already have a vague idea of how we could go into the direction of reinforcement learning. But for now, our baseline is plain gradient-based optimization. So our motivation stems from neural networks, and neural networks today are among the most powerful and popular machine learning models utilized to realize artificial intelligence. And at the core, training these networks is simply adapting weights of node connections to fit given training data. And with the rise of modern machine learning frameworks like TensorFlow or PyTorch, this task is commonly carried out by calculating gradients using automatic differentiation and then updating weights according to the gradient descent algorithm. And this is why modern machine learning frameworks like PyTorch or TensorFlow therefore come with a wide range of gradient-based optimizers that are potentially suitable for a wide range of optimization problems. Now, utilizing neural networks in some way is passing control onto the black box that is a neural network and then receiving results without knowing exact inner workings. There are exceptions, like now physics-informed neural networks, and where we try to describe the neural network with differential equations and such, but in the normal case, it's black box and we get the results without knowing these inner workings. But there are fields where intransparency to this extent is not the desired approach, or at least a model description is of interest. And trajectory planning in the field of mechatronics, it's such a field where this is potentially the case, mainly due to the fact that movement of motors and kinematic chains has immediate effect to the environment and therefore can cause harm. So we need predictive movement, which we can say calls for in some way a predictive model or explainable model. So in this doctoral research project, our motivation is not to utilizing neural networks directly, but to utilize the optimizers that come with neural network or machine learning frameworks, and instead then optimize piecewise polynomial models that are commonly used in trajectory planning tasks and optimize these models. So in this way we have state-of-the-art methods where we get updates for free in a field that is highly alive, and at the same time have explainable models where we can directly derive physical properties like position, acceleration, etc. So this is our baseline, so to speak. And in trajectory planning, we start with the most simple thing. I liked that very much yesterday. Start with the simple thing, but for me, it's although it's very simple, it's not boring. Yeah, it's just a single axis. So the simplest trajectory planning thing we've found, and was also interesting because it's very much used in industry, is that of electronic cams, and it's simply repetitive motion on a single axis that is described as mostly in this form of in a set of input points, and we need to find approximations to those points. And the approximations we find need to fulfill certain properties like continuity, cyclicity, so or periodic continuity. And by optimizing, we can directly influence physical properties here, like a velocity jerk, or we can increase path accuracy or reduce energy consumption. And our base model is very simple. So we split this input points space into equal sized segments, and we model each segment by a polynomial of fixed degree. And in our first paper that we did, we kind of showed that it's feasible, and we used standard power basis, so the representation we all frequently used. And we then represent these model parameters, so the polynomial coefficients as TensorFlow variables, and optimize them with respect to a loss function that we see later. So yeah, we used a TensorFlow then, mainly due to the fitting gradient tape context. We'll also see later that it offers, so it's very easy to do this gradient descent optimization, and it also offers a wide range of optimizers. So in this current paper that we did, so we have one out where we just saw, okay, it's feasible, and now we're trying to improve convergence behavior and reduce oscillations by exchanging this power basis with an orthogonal basis. And this has the potential benefit that orthogonal basis are beneficial for finding best approximations. And we went with Chebyshev basis, mainly due to the fact that it's very closely related to Fourier series. And we later on want to do spectral optimization, and this kind of, yeah, seemed like a good fit. So we exchanged this power basis with Chebyshev polynomials of the first kind, and those are bases for polynomials. So we then model these as TensorFlow variables, the Chebyshev series coefficients, and then optimize it with gradient descent optimization against these loss functions. So we need to have a continuous piecewise polynomial, and we need to have one that fits the input data well. So we have two optimization targets. One is simply approximation error in the least squared sense, and then we have continuity error, where we just sum up discontinuities and all derivatives that we need for discontinuity. So for us, it's like C3 continuity, because we want to have continuous position, acceleration, velocity, and jerk. So we need 4 derivatives basically that need to be continuous, and we simply sum up these errors. And by alpha, we can put more weight on either of the 2 targets. What has turned out very important is this regularization that we introduced. Basically, we found that the continuity optimization, it introduces oscillation. The more continuous derivatives we want to have. And it turned out that we need to penalize or regularize higher derivatives, because the potentially highest contributing factor to a derivative is the one of the highest order term. And if you derive, this always gets increases, and it's by this factor, at least with power basis. And it turned out to also work well with Chebyshev basis. So this is the base model. So you see, we have these polynomial segments fits 2, and with every derivative, we take this error as a continuity error, and we have these boundary points here. And this is as simple as that. It's the training loop. Basically, the TensorFlow offers this gradient tape context, so everything you calculate in here, it gets recorded, and you simply have this automatic differentiation and apply the gradients with your optimizer. And we also have early stopping to not get stuck in local optima. We'll come to that shortly. But this is basically all you need in TensorFlow. So then looking at the results, so we looked at all the available optimizers, and with just looking at the L2 error, so just approximation error, we still have a convex problem, and we have a unique solution. Therefore, we don't see it very well here, but basically it's I made it gray and dashed. Maybe that's not the best choice, but what we see is that Chebyshev is the green line versus power base is the blue lines. Chebyshev is able to get to the optimum with almost all optimizers, at least relevant optimizers. So we clearly see here that Chebyshev basis outperforms power basis. And then moving to the combined approximation target, we now have a non-convex optimization problem, because you can imagine there are many solutions for a continuous piecewise polynomial. As an example, all coefficient 0 is already a solution. And now we see, interestingly, SGD does not converge anymore for Chebyshev basis. And you also don't see the baselines here. So we did segment-wise least squares fit, and then you see the approximation. The remaining error should be somewhere here, and here it should be somewhere here. You don't see it very well. But we saw that also here Chebyshev basis is able to surpass this segment-wise optimum, and it was the only variant that achieved this. And what you also see is that the regularization is the green line versus the red one is the without regularization. So regularization is needed for this to perform well. Yeah, it's just a little animation of how such a training epoch looks like. So you see the ends kind of oscillate and with ever so decreasing magnitudes, and they have they find each other, and then it's just wobbling like in ever smaller magnitudes. But here, this is an instance where it's actually converging, but we see in many instances where it's jumping out, re-oscillating, and then landing in another local optimum. So what we basically do to guard against this is we initialize with the least squares, segment-wise least squares fit. Then we establish continuity per algorithm after optimization. So we can ensure it's always continuous. And so this is a very naive algorithm. We just take the mean of the ends and do this throughout all the segments. And we also revert to the best training epochs with early stopping, as you've seen earlier. So this is looking at how continuity error looks versus approximation error. Now, this algorithm I told you that establishes continuity afterwards is this orange line, and the blue line is segment-wise least square fit. So the upper two are very low variant data. It's like, can I draw here? So this is like something like this. It works. Nice. Oh.
But it changes your slides.
1 second. Yeah, this is something like, okay, no, it's okay.
You can use the board.
Oh, so the top ones are just something like this. So a sign it's very low variant, and the lower ones are really something like this. So here we see already that if we put segment-wise fit for 2 segments in here, it's something like this. So we have a lot of error here, and here it's only very small. And this is also what you see. What you see here. So we make a segment-wise fit. This is the approximation error. This is the continuity error. Then we do the strict establishment of continuity and land here. So this band is like where we say, okay, if we land there, it's good, because it's better like doing it the naive way. And we see that our optimization with alphas close to 0 but higher than 0, they land here. And if we establish continuity for them, they kind of going straight down. While ones that are done with alpha 0, they all are affected quite, they're affected more. So this also kind of shows we need this continuity optimization to align the ends better, so that when strictly establishing continuity, it doesn't jump. And here you see this noisy input point space. It's like, yeah, the gap is really big, and you see that most of all of our alphas make sense here, and only the alpha 0 jumps to the right, where also the naive way is. Put this into practice. Bachelor students of mine currently preparing this test bed. So we're using of BNR automation this Ecopos servo drive. It's simply taking these piecewise polynomials. We can put them straight in, and it will execute them as a CAM profile. And here we can apply different loads and measure energy consumption, and hopefully, I hope somewhere in the future, vibrations, because I really want to do like spectral optimization. Yeah, this is like the idea you saw Georg's presentation just now, and yeah, we saw maybe it would make sense to model this straight with a polynomial. Or so if we have like so here we have one output action, and we have 2 states. So it results in a 2-dimensional Chebyshev polynomial. So we can scale this like every output action is another n-dimensional Chebyshev polynomial. And so we have just very descriptive model of this policy. It's a vague idea. I'm interested in your thoughts, but it's like how we see it could connect somehow. Because I'm also in the same research project as Georg is, and it would make sense to somehow, yeah, link here. This is sort of my timeline. So the first was feasibility. We're now here with this orthogonal basis that we just want to finish now and have a paper ready. And then we can extend this loss function, of course, and want to do energy optimization, where we still have to find a baseline for that, and then spectral optimization. And maybe go more in the control theory section. We don't know yet, but this is kind of it, yeah. Thank you.
We have plenty of time, so don't hold back.
Yeah, so if I understood correctly, the main benefit of this is that you can change the loss function, or the because solving an approximation problem with piecewise polynomials in general can be solved quite quickly.
Yeah.
But in this case, you can change the reward function, for example, for energy loss.
Exactly.
Yeah, that's the main thing.
Exactly. You're more flexible and you can get more complex, and that's what we want to do in the end. So here it's, yeah, you can do this with plain equation systems, and you have an immediate solution.
Yeah.
And the more we go in that direction is where it makes more sense. Yeah. In the end, I want to be able to say, I don't know if that will work ever, but I want to say, okay, I apply a load, and that machine has a resonance frequency, and I want to filter that out and optimize it in a way that the profile counters against this unwanted frequency, for an example. Or I want to say, okay, energy consumption should be limited to X, and then it should optimize.
Any final questions?
Maybe a practical question. So this is very nice, but very small scale. Are there any plans, any ideas to extend this to real systems, which are much more high dimensional usually?
So for the time being, it's really this simple case of electronic cams that is just a real product, basically. So with this servo drive, you really have in the automation studio of Bernard, you have this cam creation tool, and basically it's like the better version of that. And you really use only single axis movement for this. But yeah, you could chain this and have multi-axis movement. This is not currently in the scope, but of course would be very interesting. Yes, if we have the silk printing as example, the bed moves. So this would be one cam, and then we have this top down. Or we could have chained axes that are linked together. Yeah, would definitely be interesting, but at the moment it's just single axis.
So, there are no further questions.